By now from the Pivot Lab, you should have seen that the essence of Newton's third law is that anytime you have two objects, you call them A and B, whenever they interact with one another, they have a force on one another, the magnitudes of those two forces are equal and they point in opposite directions. This is sometimes phrased as every action has an equal and opposite reaction, and that's true, but that's not a helpful statement of Newton's third law in a sense that modern everyday people are going to understand it. The way that we would be able to understand it nowadays is these two objects hit each other. There's going to be a force this way on A, there's going to be a force this way on B. This is F, B on A. I would probably just call this like F, B. You could call it F, A also, whatever. I don't care what you call it. And then this is F, A hitting B, right? So each of these objects feels a force. The magnitudes of those two forces are the same. They are the same type of force. So if these are two, I don't know, bouncy balls, one of them is heavier than the other. It doesn't matter if one is heavier, one is lighter, they're the same mass. Regardless of the masses of the objects, the magnitudes of the forces are the same. They're the same type of force. It could be an elastic force and a normal force, a general or applied force. They're the same type of force, and the forces are in opposite directions. So the force on A is to the left, force on B is to the right. This is how we apply Newton's third law. You've got our two objects, A and B. They're applying forces on one another. So we know two things. There's a force, we'll call it F, B on A. And when there's another force, F, A on B. They go in two different tau charts. The agent of the first one is B. The object of the first one is A. That's pretty obvious because of what I named the force. The other tau chart, the agent is A. The object is B. The way that we know that these two objects are a Newton's third law pair is to look at the agent and object. If you can take the two nouns and switch them and get the other force, then they are a third law pair. So that is your starting point. Figure out that they are a third law pair. Once you have that, then you conclude that they must have the same magnitude and opposite direction. So it's like an if-then statement, right? So if they are Newton's third law pair, then they have the same magnitude and direction. It doesn't go back the other way. You could have two forces that have the same magnitude and direction, but aren't Newton's third law pair. So for example, it's pretty common, let's say you have a book sitting on a desk and the weight of that book is 10 newtons, so that's a little bit more than 2 pounds. So if we had a free body diagram for that book, we have weight pointing down, we have normal pointing up, right? So we could write a tau chart for this. We have weight by the earth on the book, and we have normal by the table. I didn't say what it was on, I think. And that's on the book, right? So if the weight is 10 newtons, then we know in this case the normal force would also be 10 newtons because the book is just sitting on the table. But these are not Newton's third law pairs, right? What is the Newton's third law pair to the normal force by the table on the book? Well, we take those two nouns, we flip them, and the Newton's third law pair would be normal force by the book on the table, and it would be a downward pointing force on the table. Okay? This is the force that you sometimes think of as the weight of the book on the table. It's not actually the weight of the book on the table. That's a force that's between the book and the earth. It's not the table's business what that force is. Right? The force that the table feels is the normal force of the book on the table. And that's because the table is pushing up on the book. We also have the weight here. We see that the earth is pulling downward on the book. We can flip those. So the third law pair is the book pulling on the earth. The weight was pulling down on the book, so the earth must be pulling, the book must be pulling up on the earth, right? Since weight is gravitation, that's what's happening. The earth is being pulled up by the book for the force of 10 newtons. It just doesn't matter because the planet has a mass of, I think, 6 times 10 to the 24 kilograms. So it doesn't matter that you're pulling up with 10 newtons. Earth doesn't care. So, despite the fact that these two forces have the same magnitude and opposite direction, they are not Newton's third law pair forces to one another. And in fact, we could devise a scenario where these two forces do not have the same magnitude. How could that be? Well, let's say you wanted to throw this book up into the air by lifting the table. So you're flipping the table, causing the book to fly up, right? What would happen then? The net force would be up on the book. If the net force is up on the book, remember, you're lifting the table is lifting the book. So the normal force would increase, maybe it goes to, 12 newtons or something. That's the only way that there could be a net force upward on the book. So let's look at an example here. So when we're solving Newton's third law problems, we're going to be drawing free body diagrams for every object that we care about in the system. We're going to be looking at the forces on each of those objects. We're going to be looking for Newton's third law pairs and identifying those. And then we're going to write Newton's second law for each object in the system. Sometimes there's a shortcut we can do. We'll get to that in a second. So let's look at a pretty simple example. What we've got is two carts. There's a heavy cart and a light cart. And you are pushing on the heavy cart. And the heavy cart is pushing on the light cart. Okay? So we will call the heavy cart M1 and the light cart is M2. And you are pushing that way. And you see here that the floor is frictionless. So we're going to have a tile chart for each of these scenarios. And we're going to write the forces on M1 there, forces on M2 here. So I'm actually going to start with the second cart because it might be more obvious if we do. Okay, what are the forces on the second cart? Well, there's some weight and there is some normal force. So we're going to have weight by the earth on cart 2. I'm going to call it M2 just to make it simpler because that is that's the mass of the cart. So we can just call it M2. And then we also have the normal force by the floor on M2. Now, we already know that M1 is also going to have a weight and a normal force. And we know that it's not going to be the same weight and normal force as we have over here. So we can't call them the same thing. We can't have a W here and a W here because they're not the same W. So we need to use subscripts to distinguish their names. Now we also have a force to the right, because M1 is pushing on M2, making it go to the right. So we're going to have a force, let's say, like that. And I'm going to call it, there are different conventions you can put for naming things. I'm just going to call it F2. Like we wrote earlier, you could call it F1 on 2, because 1 is pushing on 2. I think that's a little clunky, so I'm just going to call it F2. So F2, pretty obviously the agent is M1, and the object is M2. Okay, now we'll think about the forces on M1. There is a normal force and a weight. Notice I'm using the subscripts to identify that these are different than these. So we have weight 1 by the Earth on mass 1. I realized that I didn't actually label these here. And then we have the normal force 1 by the floor on mass 1. Now let's think about our left and our right forces on the cart. Well, one thing that we should realize is that cart 2 is going to be pushing back on cart 1. This is our Newton's third law pair, right? We see 1's pushing forward on 2, so 2 should be pushing backward on 1. And it should be pushing by the same amount. We did 1 tick mark here, so this should be back by 1 tick mark. And I'm going to call it F1 because it's the force on 1. The agent is going to be the second cart, the object is going to be the first cart. The last thing I need to add is the force by the person, and since there is no friction, our intuition is that the whole thing should be accelerating to the right. So I will draw at least 2 tick marks here. And I'm just going to call this generally F with no subscripts. You could call it F sub P or something for person. It doesn't matter. And the agent is U and M1 is the object. So let's stop for just a second and look at what we have in the chart. For the objects, all of these are M1, which is good because that's what the free body diagram is for. All of the objects are M2, which is what we have here. Okay, so now we are going to look to write Newton's second law for each of these scenarios. So we're going to have sum of forces in the x direction equals MAX. Sum of forces in the x direction equals MAX. And we're going to fill in our forces. Everything pointing to the right gets a plus. Everything pointing left gets a minus. So we have F minus F1 equals, we're going to plug in the fact that this is M1 AX. And here we just have F2 equal to M2 AX. In order to finish this problem, well, let's just highlight something. What do we know and what don't we know? Well, we don't know what F1 is. We don't know what AX is. We don't know what F2 is. We don't know what AX is. There are some things that we do know. What we know is that F1 is equal to F2. And we know that this AX and this AX are the same. Right? If that's not obvious, these carts are moving the same. Whenever M2 moves, it's because M1 made it move. So since these accelerations are the same, that's the same variable. So we can substitute in this F2 into this equation. So we get F minus M2AX equals M1AX. and then we can finish the solution equals m1ax plus m2ax, and we get the equation that you probably could have anticipated. The force that you push with is equal to the total mass times the acceleration. This is frequently the case when you don't have any complicated factors. You just have the outside forces, right? Not the forces that are applying inside the system, like F2 and F1. Just the outside forces is going to equal to the total mass times the acceleration. And we're just going to solve for the acceleration here. So we have F over m1 plus m2, and so we have F is, 100 newtons over total mass, I think is 70. So we get 1.43 meters per second squared. Okay. So the final question is to determine what is the force of the heavy cart on the light cart. So the force of the heavy cart on the light cart is the force that we named F2. Now, I could have asked this question either way. I could have asked you for F2 or F1, and you should recognize that they are equal in magnitude. So you could solve for either one that's easiest to solve, and then use the fact that they are equal in magnitude in order to solve it. So we'll use the easiest equation, which is the one I asked you for anyway. This is equal to m2ax, and that is 20 kilograms times the 1.43 meters per second squared, and that is 28.6 newtons. We are not going to end up doing that one.